Right, for today, let's talk about, for hydrogeology, let's talk about groundwater well development. Actually, this lecture will also cover other groundwater development projects like subsurface dams and springs. Right, for introduction, right, so let's first talk about the merits of developing groundwater over surface water. Now, by surface water, we are talking about your traditional dam reservoirs and as well as rainwater collection systems. So here are the merits of developing or relying on groundwater. First is normally groundwater development, right? So it so water wells, spring boxes are typically much cheaper to develop compared to water reservoirs. But of course, water reservoirs involve much larger capacity, right? But in terms of initial investment, right, groundwater projects are typically involve smaller amounts or smaller capitals. Second point is that uh, s- surface waters are especially vulnerable to contamination as well as other detrimental effects of being exposed to the surface like evaporation. So you can expect surface water reservoirs or dams to be especially vulnerable to seasonal fluctuations in recharge. Third point, as I've mentioned before, is the evaporative loss in surface waters is large. As you have seen in the first exercise, uh, potential evaporation or rather actual evaporation is determined by the temperature and the amount of water that is lying on a surface that is available for evaporation. Now, if you have a lot of water that is exposed on the surface, you will consequently get a lot of evaporation. And yeah, that is one of the drawbacks of having surface water reservoirs. Fourth point is that dams, water or reservoirs, right? They involve inundation of large areas. When you are developing surface water reservoir or dams, you are impounding water, and this will always involve flooding of the areas upstream of the dam, right? And typically there's a lot of opposition regarding the inundation or the projected inundation when you are developing dams, right? If you will look at the news, there's a lot of watersheds that are impacted by development of water reservoirs, and also there are also cities that are or towns that are typically affected or end up being abandoned once you start developing a dam in an area. Fifth point is that by the nature of subsurface waters or the groundwater, which typically passes through your soil or your media, you normally get natural filtration of water in your groundwater. And in terms of quality, groundwater typically has a better quality compared to surface waters. And The consequence of that is that surface waters might require additional treatment and use of chemicals to for them to reach acceptable water quality standards. And last point is that surface water systems, especially dams, are not as flexible or as responsive as your groundwater systems, right? So dams are all when you're talking about dams, the water is always flowing. Although you can slightly adjust, of course, the discharge of water in your dams. It's not like in groundwater systems where you can completely shut off your well pumping or increase your well pumping as per the demand for water. All right, now let's talk about your vertical wells. Or vertical wells, of course, are your classic groundwater wells that you see. Right. So this lecture will only tackle some of the design considerations in vertical wells. The overview of vertical wells are tackled in the exercise, right? So I'm also expecting you to read a little bit uh, on the chapter on groundwater well development on the book of Sterret, which is titled Groundwater Wells, Groundwater and Wells. So it's a classic textbook, and most of the details that you need in order to properly develop a well or groundwater resource are in that reference. Now, anyway, let's focus on the design considerations of vertical wells. So you have 8 considerations. First is the drilling method. Right, for this lecture, I won't be discussing the drilling methods, but if you need a reference, you can refer to Sterret for discussion of different methods. Second is the boring or drilling and the casing diameter, right? Typically, the size of the hole will depend on the aquifer yield or the target pumping rate from the well, as and also the size of your pump. Okay. Third consideration is your depth or the depth of your well. And of course, this is mainly controlled by the depth of your aquifer, right? Or the nature of the aquifer formation. Fourth is the well screen, right? Well screen is the right. So well screen is the area that is or the part of the well that is actually open and exposed to the aquifer layer, right? And this is where your water enters your well. Okay, and well screen has important functions like preventing your aquifer formation from collapsing, as well as ensuring that the entrance of water in your well is proceeding at the most efficient conditions, which we will be discussing later on. Right, integral to your well screen is your gravel pack. Right, so this is your gravel pack, and this is basically just surrounding your well screen. Your gravel pack is like an additional protection for your well screen, right? And Let's discuss that later on. And another consideration is what we call well development. Well development is just the process of more or less cleaning up your well. Okay, so after constructing your well, this will typically involve drilling muds, as well as fines that are circulated around the hole that might get plastered around your aquifer formation. And of course, all these muds and fines are detrimental to the permeability of your aquifer formation, and they have to be removed. And that is the purpose of well development. Now, the last two, the well testing and the well pump sizing, right? So I won't be discussing these two as well, right? So you just refer to Starrett for a detailed discussion of these two elements of well design. Now let's talk about the design data and the water well diameter. First, the data that we will be using for the design of the wells, of course, should be of good quality. And the most ideal source of data is to do a pilot drilling. So we do initial drilling before the actual well drilling. And of course, we log the lithologies, the rock types, the soil types. We also take samples of the aquifer and the other layers, right? And determine their grain size distributions, as well as measure the water chemistry. Like, is the water or the groundwater acidic? Is it prone to incrustation, or like, is it possible for minerals to deposit from the groundwater and so on? Right, so these are discussed in detail in Starrett. Second point is that data, of course, is always important in any project, be it geotechnical, water resource, um, mining, or petroleum. And poor subsurface data will lead to incorrect well drilling methods in the case of groundwater well development. And note that typically aquifers uh, involve a wide variety of formations, including loose sands, especially in coastal areas or areas near your rivers. You can also have karstic formations, and all these actually pose hazard to the drilling activity itself, as well as the drilling equipment, right? Uh, so it's important to have initial subsurface data so that a proper drilling method can be used. Right? Typically, flowing sands will need a lot of extensive use of drilling casing. In some cases, it might require the use of drilling muds just to stabilize the sand, right? Now, in terms of cost, very deep wells that are in the order of 1 kilometer or 1 kilometer deep can be as expensive as 1 million US dollar. Okay, but of course this will vary depending on your location, and typically the best way to determine the cost of deep well development is to contact your well drilling suppliers or well drilling contractors. Now, in terms of the size or the diameter of your well, this is ultimately, or this is mainly determined by the target well capacity, or the target well yield, or the target pumping rate of your well. All right. Although there are other minor considerations that are factored in the sizing of your well diameter, such as, for example, a formation with low permeability, right? Low permeability, so you will typically need a well that has a large surface area when you are dealing with formations of low permeability, and this will typically require wide well diameters, okay, to maximize the area of the well that is in contact with your formation, right? Although note that um, making the well diameter larger will have diminishing returns, right? For example, an increase in diameter from 6 inches to 12 inches will only result in a 10% increase in water yield. Okay, so that is a 100% increase in diameter, but the increase in water well yield will only be around 10%. Okay, so other technologies or methods should be considered when you are looking to increase the water yield in a site. Okay, in some situations, you might have to actually uh, establish a well field or use multiple wells to increase the yield of your groundwater project. Also, well diameter should be large enough to accommodate the pump or the water pump, and the well diameter should typically be large enough to limit the groundwater velocities to a maximum of 1.5 meters per second. The purpose of this is to limit or prevent erosion of your aquifer sediments. Now, this is a table that shows different drilling methods for different types of geologic formations. Okay, so you have digging, you have boring. Boring, typically you hate boring. You also have driven methods. You also have percussion, hydraulic, air, and jetted. Okay, and these different methods have different advantages depending on the target diameter of your well, as well as the target depth of your well, and the geologic formations that are expected to be encountered. This other table shows different well diameters for various pumping rates that you are going to anticipate. Right? So note in the first column, GPM means gallons per minute. L over S is liters per second. And then you also have ID and OD. ID means inner diameter, and OD means outer diameter. Now, let's talk about the well casing. The purpose of well casing is, of course, to protect your well, right? So it serves to to ensure that only the well screen is in contact is the part of the well that is actually open to the aquifer. Okay. Otherwise, if the whole well is in contact with the aquifer and other unimportant layers, we are risking contamination from surface waters as well as contamination from other layers. So normally you will have the screen and the aquifer. Okay, so you have your screen and your aquifer, and you might have casing on top of your screen. Okay, and this is typically grouted, right? So this is typically grouted or cemented to ensure that no surface water will enter your well from other points. Okay, I mean no surface water can enter your well. Okay, so this is to ensure that the only water that is getting in your well is only coming from your aquifer. Okay, and of course the well might be also grouted from the bottom. Okay, to prevent um, leakage or contamination of water from other parts of the aquifer formation. In the United States, typically the grout from the top should be at least 15 meters, all right? So in the US, the grouting should be minimum 15 meters in length or in depth from the top. And in terms of material, we should also consider the potential contaminants that might be encountered, right, in the well site. For example, petroleum contaminants can easily permeate through PVC pipes as well as its jointing and other and gaskets. Another consideration for the casing material and the casing diameter is the lateral pressures that are exerted by the aquifer formation. This can be especially strong when you are talking about wells that are rather deep, typically wells that are beyond 100 meters and so on. Now, when we are talking about wells in bedrock, right? So there are wells that might not need any sort of casing, right? So these are what we call open boreholes. And in open boreholes, we typically just grout the weathered or the regolith zone to prevent the entrance of water from the surface. Now, another concern in well casing is, of course, the introduction or the presence of iron bacteria, right? So these bacteria are typically introduced from or coming from the surface or from the tools that are used during drilling. And the practice is that tools that are going to be used for drilling should be disinfected by a chlorine solution. Right? And you have here two diagrams that are showing different designs and different sorry. As you can see here, we have two diagrams that are showing two different aquifer formations or situations. The first one is showing how multiple casings can be used to bridge unstable or undesired formations. right? So now to show you this is, or this part is your casing and your undesirable formations, and this lower part is your aquifer, and this is your screen, right? So your water is entering through the screen and is typically pumped out to the surface. All right. Now let's talk about how the casings are actually used to bridge your undesirable formations. Right? Typically, this is, let's say this is your loose sand that is prone to flowage or collapse. What the drillers will typically do is first install a large casing, first drill a big, large diameter hole in this undesirable formation, in this case loose sand, and they install a large diameter casing, which is this one. All right. And then the second stage is to again drill a slightly smaller hole, right? This hole, and then install another set of casing. Okay. So this way we have avoided, we basically stabilized the formations by stage. So first we stabilize this formation, and then for the second step we stabilize this other formation. Now once these undesirable or unstable formations are more or less stabilized by your casing, the next stage is to drill, or finally drill, the hole for the screen installation. Right, so we drill a hole and then we install a screen in here. Okay, so that is how the drilling technology might accommodate for the stabilization and bridging of unstable formations. All right, now the next diagram is showing you a more or less a heterogeneous aquifer formation. All right, and typically when we are dealing with wells in general, of course, as a rule of thumb, typically the areas that are screened is the bottom part of the aquifer. So this part might be an aquifer, but and this part might also be a water carrying layer. But for wells, typically we only screen the bottom part. Okay, this is to maximize the hydraulic gradient. Okay, so that the water is, it will naturally flow to the bottom of your well. Now we have here an alternating sequence of sand and low permeability layers, like let's say clay and silt. Okay, and what we typically do is we install a screen that is actually open at different intervals. Okay, such that the screen is only open in the water bearing layers. Okay, there are many reasons for doing that. First is that typically low permeability layers like layers of silt and clay contain fines that can end up clogging up your well, right? And also these parts may also be unstable, especially for clays, right? So typically it is in practice safest to just screen the water bearing layers in a heterogeneous formation. heterogeneous, and unconsolidated formation. Now, the text is mentioning natural development in well, and let's discuss that in the following slides. All right. Now, again, we have two different diagrams showing different aquifer situations. The first diagram is showing a well in unconsolidated sediments that has used an under-reaming technology, right? Basically, under-reaming means you first drill a small hole, right? So you first drill a small hole, and then at the bottom of the hole, you deploy a reaming equipment that will actually widen the hole from the bottom. Okay? The purpose of widening the hole at the bottom, of course, is to, of course, number one, it is normally easier to drill, easier or cheaper to drill small diameter holes, and the casing might be cheaper. And the second reason for widening the bottom part is, of course, to give way or make room for your gravel pack. Okay, so your gravel pack is like it's like the first line of defense for stabilizing the aquifer formation as well as providing filtration. Okay, now the second diagram is just showing a well in a stable fractured bedrock. All right. All right. Now, as you can see here, we have two diagrams. All right. And the first diagram is just showing you a well in an unconsolidated sediment, which used an under-reaming technology. So what they did here is they first drilled a small diameter hole, and then they deployed a an under-reaming device that served to widen the hole at the bottom. All right. And under reaming, of course, serves to provide space for your gravel pack or uh, the granular materials that are placed surrounding your screen to provide additional structural stability of the aquifer formation as well as provide filtration. The second diagram is just showing an open borehole in a stable fractured bedrock. Alright, so the keyword here is stable and fractured bedrock. And what you are seeing here is just an open borehole, meaning this is just a hole and there is no casing. And your well is just basically relying on the fractures in your bedrock to transmit water into your well. Alright? And the other important element here is grouting the upper layer or the regolith part of your bedrock. Regolith is just your weathered part or the weathered bedrock. And grouting, of course, serves to stabilize this part as well as to seal the borehole from the surface to prevent surface waters from contaminating your well. Now, let's talk about well screen, natural pack, and gravel pack. All right. Now, take good note that the screen is basically the entrance of the water to your water well, and any mistakes in the design of your screen can severely impact the efficiency of your well, meaning you can get smaller water well yield, or you might end up with a well that might need a lot of pumping, hence electricity to operate. Right? Now, typically when we are dealing with unconsolidated materials, in unconsolidated materials, the concern, of course, is the stability of your aquifer, right? Stability in terms of internal erosion and washing away of sediments. And the workaround in that is to use small perforations or small apertures in the screen and the casing, right? So they should be small enough to prevent internal erosion. Now, when we are talking about public water supply, where water quality is the one of the priorities or the important features, right? The standard material to be used for well screens is typically high quality stainless steel, which is more or less highly resistant to corrosion. All right, now let's talk about your natural pack. Okay, when you are dealing with a more or less aquifer of a homo that is comprised of a more or less homogeneous formation, or an aquifer that might consist of just one type of lithology or soil type. Let's say, for example, just sand. What we typically do in this type of formation is to do some well development. Right? So well development will typically involve pumping the well to remove the fine sediments until we thoroughly clean the area around the screened length, right? And the only material that will be left behind are your uniformly sized and coarse grains that have good permeability, right? So these uniform and coarse grains that are left around the screen is what we call a natural pack. Okay. Now, when we are dealing with heterogeneous formations, or typically your interbedded formations or stratified soils, or in aquifer formations that are dominated by fine layers such as silt and clay, we instead rely on artificial gravel packs. All right, so we just buy or import some gravel that are specifically manufactured or specifically prepared for placement in your well. Okay, so your gravel packs are placed around your screens, and they are used instead of trying to develop a natural pack. Okay, so natural pack might not be possible to develop in a formation that has a lot of fines, right? And another consideration in your well screen is the size of the openings. And typically the size of the openings should be small enough to prevent internal erosion. All right, and that sizing will be based on the grain size distribution of your aquifer. And we will discuss that later on, how we determine the well screen size openings. All right. Now, other design parameters like the percentage of openings, or how much area of the screen should be open, and then the screen diameter, as well as the length of the aquifer that has a screen, These are typically selected simultaneously to ensure that you are having a maximum well yield, as well as as well as these should be selected such that the well efficiency is maximized. And lastly, these parameters should also satisfy the need for structural integrity of your screen. And this is a special concern when you're dealing with deep wells. Now, to actually properly obtain your optimal length of screen, as well as the area of the screen that is actually open, all right, we typically optimize these parameters by ensuring that the entrance velocity of the groundwater at the screen is acceptably low. All right. What we typically need is that the groundwater entrance velocity should be low, like zero point 0.1 feet per second or approximately 0.03 meters per second. All right. This should be slow because high velocities will actually introduce turbulence, or more or less a random motion of your water particles. And turbulence will result in loss of energy, right? And when you lose energy due to turbulence, this will typically necessitate additional energy or effort exerted by your well pump. And other problems can also be accelerated by high entrance velocities like corrosion and incrustation. Right? And of course, this can also worsen your problem of sand flow or sanding, or the flowage of sand into your well. Alright, so our target or the ideal entrance velocity is zero point 0.1 feet per second or zero point 0.03 meters per second. Or this is also equal to 6 feet per minute. Alright, so using the equation above, uh, for example, if you have a site that has an aquifer yield of 10 gallons per minute, so meaning that is the target pumping rate, right? 10 gallons per minute. And of course, our target screen entrance velocity is zero point 0.1 feet per second. All right, so we can calculate the optimal screen parameters to satisfy this velocity criteria. So we have Q, and we also have entrance velocity or VE. All right, and from there we can calculate the ideal well parameters. All right, so I think the calculations here are incorrect. I forgot to multiply the quantities by 7.4. But anyway, this should be actually around L should be approximately equal to L should be actually approximately equal to 13.4 feet. So this is incorrect. This is also incorrect. So L here should be actually closer to, let's see, 6.7 feet. All right. All right. So you can have a lot of you have actually an infinite number of combinations that can satisfy these conditions. And of course, you also have other considerations in choosing your well screen design parameters like the like the actual thickness of your aquifer. All right, so we will be discussing this part later on, like how long do we typically how long is typically the screen, all right? And also the effective aperture area will also of course depend on the size of the borehole, right? So typically when you have a big borehole, you can easily have a bigger aperture area, all right? Now let's talk about the sizing of the screen aperture or the size of the opening of the screens. So if this is your screen, this will have apertures or openings, and they typically have a crisscross pattern. And if you zoom in, this will just will actually consist of multiple tiny openings. All right, so as I have mentioned earlier, the size of the screen apertures will depend on the grain size distribution of your aquifer formation. Now we have a parameter called uniformity coefficient or CU, and this is just obtained by dividing your D60 by your D10. So some of you might not be familiar with the terms like D10 and D60. So let's go to this table first. All right, so this table is showing you three columns. The first column is the DN size of the soil sample. All right, so DN will just mean the size in which a certain percentage of your soil sample will pass through. All right, so if you have a D10 size, so let's say your D10 size is 1 millimeter. So this D10 size is the size where 10% of your soil sample or your aquifer sample will pass through this size. All right. So if 10% pass through that aperture, it also means that 90% of the soil is actually retained or does not pass through that size of opening. Now let's say we have another size which is D20. All right. And let's say, for example, from the grain size analysis, the D20 is, let's say, 3 millimeters. All right. So typically your D20 will always be larger than your D10. Your D40 will be larger than your D20, and so on. So for your D20, that means that a 3 millimeter opening will allow 20% of your samples to pass through. And that will also mean 80% or this size will allow 80% of of the soil grains to be retained. All right, so basically you get the pattern. I mean, the bigger the D number, you typically have a bigger size of opening, and you have more sediments that you have a bigger percentage of sediments that are able to pass through with this size. All right. Now for a uniformity coefficient that is larger than 6, the screen aperture size should be able to retain 30% to 40% of the aquifer sample. So that means we should look for the size, for a size that is able to retain 30 to 40% of your sample. So you are looking here down like D60, for example, will allow passage of 60% of your samples and will retain 40%. And then you also have D70, which will allow passage of the 70% of your samples and retain 30%. So from there, to be able to retain around 30 to 40% of your aquifer soil, you need a size of D60 or D70. And this size is just determined from your grain size analysis. Alright, so I won't be discussing how this is obtained. I believe this is discussed in your soil mechanics class. But alright, so these numbers are just obtained from your grain size analysis, from your grain size curves. Now, for uniformity coefficient of less than 6, you typically the requirement is that the screen size should be able to retain around around 40% of your formation. So that is around the 60. Now, when you are dealing with waters that are corrosive, or let's say, for example, you are doubting the results of your lab test, the safe way to go around this is to increase the target retention by 10%. Or in short, the workaround for poor quality data or for corrosive waters is to use smaller sizes for your screen. Okay, for example, a D40 will be a D30 and so on. The reason for this is that corrosive waters, of course, eat away your screen material. So corrosion will lead to loss of your metallic material. So corrosion over time will actually widen your screen aperture area. All right, so that is the reason for the use of smaller sizes. Now, when you are dealing with a formation or a heterogeneous formation where we have more or less fine sand or silts that are overlying a sandy material, all right, so this is silt and this is sand. What we typically do is we use the aperture sizing for this upper for the finer one. All right, so if the aperture size requirement of silt is, let's say, point 0.1 millimeter, we use that in the lower layers as well. Now, the reason for this is that if you use a bigger aperture in in your sand, there is a possibility that the finer overlying materials can actually flow down, all right, and actually exit through your bigger apertures below. So you typically have to extend it down below. Now, let's see. Now, let's talk about gravel packs or your artificial gravel packs. So These criteria above are again for naturally developed wells, meaning you don't use gravel packs, you just rely on your natural packs. When you're dealing with artificial gravel packs, you have a much simpler criteria, and all you have to do is to get a screen aperture opening that is able to retain between 85 to 100% of your gravel pack material. And 100% retention will simply mean that the smallest grain size of your gravel pack should be more or less equal to the size of your aperture, or your aperture should be slightly smaller than the smallest grain in your gravel pack. Alright, now let's talk about the screen length and screen intervals. And Driscoll 1986 has the following recommendations. For a homogeneous unconfined aquifer, right? So let's say this is your aquifer and it is homogeneous. For an aquifer that is less than 45 meters in thickness, let's say 30 meters, sorry. The the screen interval is the recommended screen interval is around one third to the bottom or one third to the bottom half of the aquifer. So if this is your well and this is the limit of your aquifer, alright, so if this is your aquifer and this is your well, the recommendation of Driscoll is to screen either one third or one half of the bottom of the aquifer. So one third is about 10 meters from the bottom. All right, so that is 10 meters. Or you can also do the bottom half of the aquifer. So that is around 15 meters from the bottom. Right, so that's how it works. Now, if your aquifer is more than 45 meters in thickness, you can go ahead and screen the bottom 80% of the aquifer. All right. And the intention here is to ensure that the pump is always submerged in water. All right. So this is to preserve the life of the pump as well as to ensure that the drawdown involved is minimal. All right. Now, when you're dealing with a heterogeneous unconfined aquifer, we basically use the same criteria as in letter A. Although in a heterogeneous aquifer, we only count the permeable layers. All right, so we just count the thickness of all the permeable layers and just we take the one third of that or one half of that, and then we just screen that one third or the bottom one half of your permeable layers. Now, for homogeneous confined aquifer, the screen length is around, or the target screen length is around 80 to 90% of the thickness of the water bearing layer. So more or less the almost the whole thickness of your water bearing layer. And then for your heterogeneous confined aquifer, Of course, we also screen between 80 to 90% of the permeable layer. And then there are also additional things to do if there are fine layers that are overlying your coarse material or like sands. So if there are fine layers overlying coarser grains, we typically have to extend the screen for the fine materials downward to your coarse material. So the purpose of this is to prevent the fine materials from flowing downward through the bigger apertures in your course material. So the purpose of it is to prevent sand flow or flowage of your fine materials or internal erosion. Also, we also have to ensure that the size for the screen is not more than double, or the slot size for the coarser material is not more than double the size for the overlying fine material. So what we do here is we might have to gradually increase the slot size if there is a drastic change in grain size. Now let's talk about gravel packs. All right, gravel packs are typically ideal for aquifers with uniformity coefficients of less than 2.5. All right, so these are your right uniformity coefficient of less than 2.5. You're talking here about soils that are more or less uniform in size. Right, so a CU that is equal to 1 is more or less a perfectly uniform soil in terms of size. All right, so the criteria here is to ensure that the D70 of your gravel pack must be 4 times to 6 times the size of the D70 of your aquifer. So for example here, the D70 of your formation material is around zero point 0.2, all right, from the logarithmic scale. Zero point 0.2 millimeters, that is the D70. So the D70 of your gravel pack should be around 4 times or 6 times of that zero point 0.2 millimeters. So we need a gravel pack that is sized around zero point 0.8 to 1.2 millimeters. All right. So if we look at here, the gravel pack size or the gravel pack D70 is actually around let's say around 1.05 millimeters, which is within this ideal range. All right. So basically, this is how you get your D70, D10, D30. So all you have to do is to look at your gradation or your soil gradation curves. All right. So this axis is your this y-axis in your right side is your percent passing, and then this axis on your left side is your percent retained. All right, so if you need D70, all you have to do is to look for 70%. All right, and then intersect that line with your sample results, and then project that line downwards to your size axis. All right, so let's say you need to find out the D40 of your formation sample. So D40, you just project that line to the curve of your formation material. And from the intersection, you project it below. All right. Sorry, I think there is a typo in the book itself. So forget what I discussed earlier in this slide. All right, so just focus on this axis. So this is your percent passing. All right, so at when you have a very big grain size, let's try to extend this size plot chart for easier visualization. So let's say, for example, at 10 millimeters, 10 millimeters grain size diameter, you will have 100% passing. Meaning at 10 millimeters of aperture, all the soil samples will easily pass through that size. Now, if you have a size of around 2, 3, 4, let's say zero point 0.4 millimeters, all right, so at zero point 0.4 millimeters, you get 0% passing. All right, so meaning that is zero point 0.4 millimeters is smaller than the smallest green particle in your sample. All right. So typically, the bigger the green size, the bigger the percent passing. All right. So that's how we can more easily remember this convention. All right. So now let's apply that to this formation material sample. So the D70 of your formation material should be actually here. 70% passing, intersect it with the curve, and then project it downwards. What you get is 0.2345, 0.5 millimeters. All right. Now, multiply that by 4 or 6, you get 2 millimeters to 3 millimeters. All right. So the D70 of your gravel pack should be around in that range. And what we are getting here is actually 2 millimeters, which is still within the criteria, right? All right, so that's how we basically select the sizing of your gravel pack. And in addition, here, if you are using a gravel pack, the gravel pack should be more or less uniform. Like the uniformity coefficient of your gravel pack should be less than 2.5. In practice, normally the most preferable gravel pack is a gravel pack with a perfectly uniform size, meaning the gravels in the pack just have one size. And for that, you have a uniformity coefficient of 1. Now, let's talk about well development. All right, and this involves well development is basically cleaning up the borehole. As you may know, well drilling involves a lot of mess like compaction of the soils, smearing of clays around the borehole walls, insertion of fines into the cracks and crevices of your aquifer formation, and of course, these all serve to clog up or reduce the permeability of your aquifer. And the objective of well development is to basically remove all those fines and all those mud that might be affecting your well or your aquifer. And for new wells or for newly constructed wells, development should always include backwashing or the movement of water in both directions of the screens. So it means pumping in water and pumping out of water to ensure that the water is actually moving in and out of your screen. And sometimes chemicals are used, and these typically include mud dispersing agents such as polyphosphates. And if you're dealing with limestone formations, you might also need acids. All right, so acids are there to dissolve or widen the fractures around your limestone formation. And then finally, the criteria for determining whether your well development has succeeded is as follows. So you should do a 2-hour pumping at your design discharge, and at that pumping rate, the sand content should be less than 5 milligrams per liter. And this should be measured by at least 10 samples. And then there should be also no significant increase in specific capacity or specific discharge for at least 24 hours. Or it means that the pumping rate or the discharge should be more or less steady for 24 hours. Now, for the methods used in well development, you have pumping, surging, fracturing, and washing. And note that there is also a common method which is called overpumping, and this involves pumping water into the well. Although the problem with overpumping is that it's not fast enough to completely remove the fines in your well. So overpumping is a common method, but it's not the most effective method to use. Now, another method that is common is the pumping using compressed air. All right, so they what they do is they try to inject compressed air into the formation. Although the problem here is that pumping in compressed air, especially when you are dealing with stratified aquifers that contain impermeable clays can actually cause an airlock, and this can cause your formation to collapse. Now, the most efficient method water for well development is actually the use of high pressure water or air jetting, which is done in combination with simultaneous airlift pumping. And what happens here is we lower a jetting equipment. All right, so typically your jetting equipment is a tool with a nozzle. All right, it has a series of nozzles, and it shoots out water or air from those nozzles. All right, so it goes out in high pressure, and this can remove the fines around your aquifer crevices, cracks, and aquifer pores, so that you end up with water inside your well. So you actually end up dislodging all those particles, and they just end up being suspended in your water well. All right. So once you have suspended most of your fines in your water well, the next step is to do an airlift pump so that you can remove the water with fines out of the well. All right. Now there are other considerations in well development. For example, sandstone aquifers can be quite problematic, especially if you're dealing with poorly cemented sandstone that are friable. All right. So Friable sandstones are typically difficult to subject to water well development because they are prone to loosening. They can actually collapse, right? So or undergo sanding. So typically the preferable method here is to actually use small sized screens to ensure the stability of the hole, even if it actually reduces the specific capacity of your well. Now, another method for well development is hydrofracturing, and this can be used in new and old wells in consolidated formations. So, typically, your rock formations. And hydrofracturing involves extreme pressures, and of course, extreme pressures loosen up all your fractures, as well as they can also induce fracturing within the formation for increased permeability. All right, so this is how hydrofracturing works. You basically just inject water at high pressures, and this typically involves a bladder or a inflatable packer to ensure that the pressure is just directed towards the fractures. All right. Now, acid can also be used, of course, for well development and well stimulation, especially in limestone and dolomite aquifers, and as well as in some semi-consolidated aquifers with some calcium carbonate cement. All right. So acid serves to dissolve your carbonates to enlarge your voids in pores. All right. So the end result of using acid, of course, is to increase the overall permeability or hydraulic conductivity of your aquifer. Now, let's talk about collector wells or your horizontal wells. All right. A collector well is basically a huge vertical well. So you have a big vertical well, sorry, and then you have horizontal wells that are protruding from your huge vertical well. Right? So the purpose of this, of course, is to maximize the extraction of water from your aquifer. All right? And horizontal collector wells are basically or chiefly used in alluvial aquifers, especially those in aquifers around large rivers, as well as other unconsolidated and consolidated rock aquifers. Although collector wells are really commonly used for aquifers around large rivers where you have a lot of recharge and you have a lot of water that can be extracted. Other uses of collector wells include ASR or aquifer storage and recovery programs. All right, where in ASR you are artificially injecting water into your aquifer, so you will need a collector well that has a high capacity to inject a lot of water into your aquifer. All right, and this can also and collector wells are also used in coastal areas where you are actually using aquifers to filter out salt from your seawater. Now, in terms of construction, as I've discussed earlier, you basically have a large caisson, a reinforced caisson, or a huge hole that serves to pump out or pump in the water. And then this one has several projections, or these projections are essentially just horizontal wells that are used for collecting water around the central well. All right. The advantages of collector wells, of course, include situations where your aquifer formations are stratified. So when the formation is stratified, you can easily select, or you can easily target certain layers for extraction. And of course, in terms of hydraulic efficiency, you can easily design the well to ensure that the hydraulic gradients at are optimal. Right, now let's talk about subsurface dams. All right, subsurface dams are essentially dams that are underground. And you see here three different figures. And in the first figure, you essentially have a flat area, and you have your groundwater in here, and you have your catchment at the upslope. And what they do here is they insert an impervious structure like clay or concrete that can serve as your subsurface dam. And in effect, it serves to impound the groundwater behind the dam. Now, in terms of advantages compared to surface dams, there are several advantages for using subsurface or underground dams. First, of course, is that subsurface dams basically have water that is in the subsurface. So you have minimal amount of water that is exposed to the surface for evaporation. So you more or less have very negligible evaporation loss in subsurface dams. Second point is that subsurface dams barely affect the land use above the reservoir. In fact, subsurface dams can even improve the vegetation in the overlying ground, right? Unlike in surface dams where you end up flooding the whole area, all right? Third point is that you have natural filtration in subsurface dams. So you have better water quality. And then fourth point in subsurface dam is that you don't have the problem of sedimentation. All right? So this is a major problem in dam reservoirs or in surface dams. You typically lose a certain amount of reservoir capacity over time due to the deposition of sediments in your dam. Now, for the case of subsurface dam, it's not an issue. So you more or less can expect a longer lifespan for your subsurface dams. You also have no danger of catastrophic loss, right? And then, of course, the overall impact in the environment is much lower. Now, the advantages of subsurface dams include, of course, you have a storage capacity that is difficult to estimate, and then you also end up intercepting groundwater flow downstream. So, if you have wells downstream of the subsurface dam, they might end up having reduced well yield. Now, there are two main types of subsurface dams. You have your subsurface dams and you also have your sand storage dams. Now, your subsurface dams are essentially you have an impermeable structure constructed in the underground. So this could be concrete or clay, and it serves to impound the groundwater behind it. Okay, and the effect of groundwater impoundment is of course you you end up raising the water table, so you get more stored water, and you also stabilize the groundwater table level in here. Now, for sand storage dams, this is a lot more sophisticated. What they do in sand storage dams is you first build an impoundment in the surface, all right? So you have a small dam in the surface that is anchored on your bedrock, and you might also need an impervious core. So this is typically a clay inside a trench to prevent your subsurface water from escaping below. And then what happens here is they construct a series of channels that divert floodwaters into this impoundment, all right, such that this part gets flooded and it ends up depositing a lot of sediments, particularly sands, all right, until this first level fills up with sand deposits. All right, after that, after filling up the first stage, they add another impoundment, another level of impoundment, and again, they channel flood waters into this impoundment so that it ends up depositing a lot, even more sand. So they just repeat the process continuously until they have basically a step that has a lot of sand deposits. And that series of sand deposits can store water. All right, so this can store groundwater, and of course, this can be exploited later on by drilling in wells or inserting irrigation pipes underneath. And this process typically takes 4 years to complete. All right. Now, the last type of groundwater development involves springs. Right? So this is just a brief discussion. There are three types of spring capture. First is the use of minimal or no artificial intervention. So basically, we just tap the spring by putting in some hose or pipes, and we just use the spring as is. This is very common in the provinces where most of the springs are tapped by a DIY series of pipes, right? Although this is not really preferable because it does not provide protection from water contamination. The second type is in engineering intervention, basically for protection of the water source. So these involves fencing around the spring, putting some covers to ensure that the spring is actually protected from surface contamination. And then the third is the use of engineering intervention to actually enhance the discharge of their spring. All right, so this involves constructing collector trenches. So this will typically involve digging around the area of the seepage and creating a channel to ensure that the whole seepage area is actually collected and concentrated on a single spring box. All right, so your seepage is typically trenched. You typically dig a trench around the seepage, and then you divert all the seepage into a central spring box. Now, for potable water supply purposes, the minimum is to have complete enclosure for your spring. Of course, the purpose of it is to prevent contamination from the surface, as well as to provide access for cleanup, maintenance, and as well as water distribution. All right, for a typical construction of a spring or a spring box will have one side of the spring box open for inflow in the case of a spring that is actually exposed vertically. All right, so if this is your ground surface, if this is your ground surface and this is your spring, so it's basically exiting from from a vertical surface. You basically have to construct a spring box that is open at this side. All right, so the spring can enter the spring box in this side. Now, if your spring is actually issuing from a horizontal surface, all right, so let's say this is your surface and this is your spring. So it is actually issuing out from a flat ground or from a horizontal surface. Then your spring box should be open from the bottom. All right, but in all cases, the spring area should always be stabilized by a gravel pack or rock fragment. So you'll typically have a gravel pack in here, and the purpose of your gravel pack or your rock fragments, of course, is to slow down the discharge or the velocity of your spring to prevent for any further erosion. All right, so that this part won't end up being eroded out. All right. Now, a spring box will also typically have three pipes. One pipe is for water overflow. All right, so if this is your spring box, this box will typically fill up with water. Okay. And in case of an overflow, there will always be an overflow pipe at the top part so that if the water rises, it can exit through the top overflow pipe. And then you will typically also have a bottom pipe for clearing out the spring box. So in case the spring box gets a lot of algae or bacteria build up, this can be drained out from the bottom and the spring box can be sanitized. And then the third pipe is for water distribution. So this pipe will typically be located at the middle part of the spring box. And this is typically connected to your household or a treatment facility to ensure that the water quality is meeting your acceptable water quality standards. Right, so this is a typical schematic of a spring box. So you have your aquifer in here, and this part is open, this part of the spring box. So this is your spring box, right? And this box is open on this side. And these are your gravel or rockfill insert to stabilize your aquifer formation to prevent your aquifer from being eroded or being from washing out. So the water enters here and you typically have a water table that is being maintained inside your spring box, and then you have an overflow pipe, and then you also have a drain pipe or an under drain in case you have to clean up the spring box. And then you also have your water distribution pipe that is connected to your household or your treatment facility. All right. So basically, that is your the basic elements of your spring box design. You may also have to provide surface water diversion. The purpose of this is to prevent surface waters from entering your spring box and contaminating the water inside the spring box. So these are ditches or trenches that are located upslope of your spring box, and they are actually diverted away from your spring box area. Right, so that is the end of the lecture for this session. For further references, you can read up Kresik, and for the details of your wells, you can read up the chapters of Steret. I think that's chapter 9 or 10. Right, thanks for listening.